This next unit focuses on thermodynamics, and the key question this chapter is going to investigate is the reaction spontaneous? Today we call it thermodynamically favorable, as seen by the underline there. When you explain something on the national exam on a justification for this problem, try to use the words thermodynamically favorable, or if you see those words, you know exactly what that means. Now, to look at a reaction, if it's favorable or not, we have two different things to consider. The first is going to be delta H, which is enthalpy, which we've already covered. Enthalpy is looking at the heat of a reaction. Now, if a reaction is going to be spontaneous, thermodynamically favorable. Now, I'm going to use the word spontaneous a lot just because it's shorter for these video lectures, but the words you want to use is thermodynamically favorable. A reaction that is got a negative value for it typically is spontaneous. So if it has a positive value, then we would say it's not thermodynamically favorable. Entropy, which is given by delta S, here number 2, this is looking at if a reaction is spontaneous or not in terms of does it have more order or less order? Is it more chaotic or is it less chaotic? And for the sake of this unit, actually in the sake of thermodynamics, down in number 2 here in the very bottom, entropy is favorable when something is led to a less ordered or a more chaotic state. The universe favors chaos, which leads into theoretical physicists and chaos theory and everything else, the death of the universe, but that's beyond this point in the scope of this lecture. So for reaction to be spontaneous, we're looking typically at the heat of a reaction, delta H, and then the entropy, the chaos of the system, delta S. Finally, in a couple lectures from now, we'll talk about delta G. Delta G is called Gibbs free energy. Gibbs free energy takes into account both the enthalpy, the entropy of a reaction, puts it all together, along with considering temperature and pressure conditions to compute a value, which then overall tells a reaction is spontaneous or not. So currently, the next few lectures, we're going to focus on entropy, which is delta S. Now, to review again, enthalpy reactions are those, if it's an exothermic reaction, it will be typically spontaneous or thermodynamically favorable. Again, remember your potential energy diagrams. Okay, down here is the course of the reaction. If a reaction is exothermic, okay, here's the energy content of the reactants. Okay, energy content of the products would be lower. Okay, the reaction would go up and then would come back down. But overall, the enthalpy of the reaction is the difference in the height of the reactants to the products. In this case, we would go down, and therefore the delta H, or the enthalpy of the overall reaction, would have a negative value. Okay, or the other connotation you can see is it would be less than 0, which indicates that it's an exothermic reaction. If a reaction is exothermic, the energy that is expelled as the reactants form products, that energy will self-propel the further reactions of more reactants forming products, and that's why these reactions tend to be go to completion, because they can provide the energy for it. The initial phase of the part, because the energy goes up, we know the hump comes up from the reactants. That little increase in energy we all know is called the what again? The activation energy. If the current temperature and pressure doesn't overcome those initial energy confines to break bonds, the reaction still won't necessarily occur, and that's where Gibbs free energy comes into it. Taking into account all factors, including temperature and pressure, will we get the reaction to go to, if it says if it's spontaneous, thermodynamically favorable, the reaction will. If I mix the chemicals together or the component in the flask, the reaction will go to completion. And that will mean that there's enough energy in the reactants that they can overcome the activation energy and form products. Endothermic reactions tend not to be self-supplying because they continually need more and more energy placed into them to keep them moving forward. Entropy, as I said before, is looking at a more chaotic system. And therefore, the change in entropy, again given by the triangle, delta S, if the reaction has an increase in entropy, okay, greater than 0, or if the entropy, change in entropy has got a positive value, the reaction is also thermodynamically favorable. Is there an increase in chaos, or an increase in entropy, which is the randomness of a system? All right, turning the pen to page 2 of this lecture. The more random or disordered a system, the more or greater the entropy of the system. Now, the way we can compute that is right here in B, is just like H. If you remember back from Unit 2, we calculate the enthalpy of a reaction. One of the ways we could do that, and again, that little not symbol means standard state, which is at 25 degrees Celsius for thermodynamics and 1 atmosphere of pressure. The enthalpy of a reaction is given by taking the sum of the heats of formations of all of the products, adding them up and subtracting them from the sum of all of the heats of formations of the reactants. How much energy of the reactants products are there when they're formed from their elements in standard states? That we can use those values in a thermodynamic table to calculate the overall enthalpy of a reaction. We can do the same for entropy. Okay, so for entropy, if we look up the entropy values, and I've placed those values, I've placed some thermodynamic tables on Canvas. You can use those to review those and use those numbers to do all the problems in the homework packets I'm going to supply you in Canvas. So we can calculate the entropy of an overreaction by, again, looking up the entropy values, entropy formation values of the products, and sum up all the entropy values of the reactants, and the difference in those will give us the overall entropy of the reaction. If the enthalpy, delta H reaction, is negative, and the delta S, the entropy of a reaction, is positive, both of those are thermodynamically favorable, which tends to tell us that that reaction, if I were to have it at those states, the reaction will go to completion. For example, if I place an ice cube out into a room temperature, it automatically melts. It is thermodynamically favorable because we're looking at both the state of the material increasing its entropy and also the room temperature is warmer than the ice, and therefore energy naturally flows into it, causing it to melt. States of matter are the critical way of determining the entropy of a system. If they ask you on the national exam to predict the entropy of a reaction, all we really have to do is look at the states of all the reactants in the products. If the products have more entropy, then the entropy will increase as the reaction proceeds forward. Going from a solid to a liquid. Liquids have more entropy than solids. Why? The particles have more movement. Solids can only vibrate. Liquids have the ability to both vibrate, rotate, and move and flow past one another. Therefore, the entropy going from a solid to a liquid will increase. There's an increase in entropy, or it has a positive value. Same thing going from liquids to gases. When a liquid goes to a gas, there's also an increase in entropy because the particles have more randomness in how they can move. In a liquid, they are confined to the liquid themselves. But in a gas, because there's such low IMFs, the particles can move on forever, and with low IMFs, they can travel on until they bounce off of something, like the container walls. So, when we go from a solid to a liquid to a gas, there is an increase in entropy as we go from left to right. Okay. Also, there is a much larger significant increase in entropy going from a liquid to a gas state. Therefore, the gaseous state is the key state to identify in any chemical reaction. If we are producing more gas on the product side, the entropy will definitely be increasing. If there's less gas on the product side, then the entropy will definitely be decreasing in the reaction. Another thing to consider is the temperature of the reaction. If we increase the temperature of the reaction, there is an increase in entropy. Why? The molecules, as we know, looking at the KMT models, show the molecules are moving faster, and because they're moving at a higher rate of speed, there are more collisions, there are more randomness in the sample. So increase in temperature also increases entropy of a material. Okay. So, as stated before, number 4, if there's an increase in the number of moles of gas in a reaction, the entropy of the reaction will be increasing. So if you're asked to predict a reaction, simply look at the states of matter, and that'll allow you to do that. So on your homework problems, when you start them, if it asks you to predict the sign of S, entropy, look at the states of matter to do that. One of the laws of thermodynamics, there are 3 laws of thermodynamics. One of them, I can't remember now if it's the second or third, is this. The entropy of a purely crystalline solid at 0K, absolute 0, is 0. The only way you can have a 0 entropy of a material is if it's a purely ordered crystalline solid at 0K, because at 0K, there is no movement of the molecules, or even the electrons, and therefore they're put in a perfectly ordered system where there is no movement of any kind, and therefore it has zero entropy. All right, so let's look at a couple examples of this and how we can predict a sign of entropy. So take a couple seconds there and look at A and B and C. So in A, taking dry ice from a freezer where its temperature is -80 and allowing it to warm to room temperature, what do you think will happen to the entropy of the system? Will it be an increase or a decrease in the entropy? You are correct. The entropy will increase as we go from the dry ice from the -80 to room temperature, because it's going to go from a gaseous state to it'll go from a solid state to a gaseous state, because dry ice sublimes. Sublimes means it directly goes from a solid to gas. It doesn't get wet. Going from a solid state to a gaseous state, we see an increase in entropy because the particles in the gas state have more randomness and movement and can move much more so than solids can. Let's look at letter B, dissolving bromine in hexane. So we're going to take bromine, which is a diatomic liquid, and we are going to mix it with hexane, which is also a liquid. Excuse me, it should be C6, and this should be H14. When we make mixtures of things and put them together, there is a greater entropy in the system, because the molecules, when they're by themselves, they're more ordered. All the particles are the same. But when we mix them together, now we have more different types of reactions. We have an interaction with bromine molecules with themselves, hexane molecules with themselves, but now also with each other, and therefore there is an increase in the entropy of the material. Lastly, let's look at C. Condensing gaseous bromine to liquid bromine. Now we're going from a gaseous state to a liquid state. What do you think is going to happen to the entropy? The entropy will decrease because we're going from a less ordered state of matter, gases, to a more ordered state of liquids. Therefore, there is a decrease in entropy. So again, whenever you do these problems, look at states of matter. Now mathematically, which will be the focus of the next lecture, we have tables of values to look at, and again, thermodynamic constants are 1 atmosphere and 25 degrees Celsius, not STP. This is not gas laws. Almost all materials, even elements and compounds, they will have values of entropy. Unlike enthalpy, enthalpy values for elements is 0 at standard states. But entropy values, all materials have an entropy value, because if we're not at absolute 0, their molecules and their particles are moving. Protons, electrons, especially electrons, are moving, and therefore there's entropy. So what we'll do again in any of the values is up here in the top again. If I'm asked to calculate the entropy of a reaction, I'll be given a table of entropy values, and I plug those in and I calculate the entropy of a reaction. If I'm looking at how to predict the entropy of a reaction, we look at states of matter. Hopefully this lecture will provide some insights on what you're looking at. The next lecture will take now that reaction up there in letter B, and we'll start plugging numbers in and start computing values. Again, I've supplied a table of all thermodynamical values, delta H, delta S, and delta G, which you can then use on all the values of all the homeworks coming up in this unit.